Hi, we are now going to talk about the AI SPRINT Drift Detector. The AI SPRINT Drift Detector allows to automatically detect data drift at runtime, enabling the collection of new dataset after the detected drift to adapt existing models based on neural networks to the new data distribution. The motivation is the need to update the existing components to work with the new data distribution and to provide standard drift detection algorithms ready to be deployed. Without AI Sprint, the user of the AI application has no automatic ways to detect data drift at runtime. An AI expert must be involved to provide specific drift detection algorithms, and there are no mechanisms to collect new data after the drift is detected, thus making it difficult to adapt existing models. With AI Sprint, the user has a simple interface to choose among a set of predefined detection algorithms ready to be used by the drift detector. The drift detector is automatically deployed and allows to monitor the set of metrics defined by the user and available through the AI Sprint monitoring subsystem. The AI Sprint Drift Detector periodically executes the selected detection algorithm, and at runtime, each component of the application can interrogate the state of the monitored metrics and can decide to store new data in the case of drift. Let's introduce the application that will be considered in the next demo. It consists of a time series forecasting application, which takes as input a time series of 300 samples and predicts 300 samples in the future. It is composed by two components: the identity component, which computes the mean of the input sequence and stores it to the InfluxDB, and the forecasting LSTM, which is a component using a low short-term memory network for forecasting. The AI Sprint Drift Detector detects data drift by monitoring the mean metric stored by the identity component. During the demo, we are going to use the AI Sprint design to prepare the application for the deployment, followed by the Toscarizer to generate the Docker images of the components and the corresponding Tosca files. Then we are going to deploy the application components together with the drift detector, and we use a simulated time series dataset to feed sequences to the application at runtime and to demonstrate the execution of the drift detector. We intentionally change the distribution of the input sequences to cause a data drift detection and the automatic collection of new data, to be used to adapt the forecasting LSTM network to the new data distribution. The application is composed by two components, the identity component and the forecasting LSTM component. The identity component simply propagates the input sequence to the next component, which is in charge of performing the prediction. The forecasting LSTM is an LSTM-based neural network which takes 300 samples as input and forecasts the value of the next 300 samples. The input sequences in this demo have been simulated in order to demonstrate the use of the drift detector. So basically, we generate a very long time series by changing the distribution of the data at a certain point of the sequence. Then the sequence is split in time windows, which are sequentially fed to the min.io bucket to trigger the execution of the application. Here we can observe a demonstration of inference performed by the forecasting LSTM model after the change of data distribution in the input sequences. As it can be observed, the model is not able to correctly predict the future values of the sequences. The goal of this demo is to demonstrate the capability of the drift detector, which is in charge of detecting the change of data distribution, in order to enable the collection of new data after the change. This new data will be used to retrain the forecasting LSTM model in order to adapt to the new distribution. In order to do that, we must define the metrics that must be monitored by the drift detector. In this case, it is the mean of the input sequence, which is computed by the identity component. We can observe the time series generated by the monitored mean, computed on the input sequences, exhibits a change of data distribution at a certain point. The goal of the drift detector here is to detect this exact point at runtime. To this end, the AI SPRINT Drift Detector, which has been deployed on the last computational layer, is performing periodic query to the InfluxDB in order to get the values of the monitored mean metric. Then it performs statistical algorithms in order to detect the data drift and updates the state of the metric. Each component of the application is then able to read the state of the monitored metric by using the utility function which is called the getMetricDriftState, and based on the value of the state of the monitored metric, decides whether to save new data to the local output min.io bucket. Let's inspect the implementation of the two components, starting from the identity one. As we can see, it simply checks the status of the monitored metric, and if it is not in the drifted state, it computes the new mean and stores it into the InfluxDB, and then it stores to the output bucket the input sequence by appending the notedrift suffix at the end of the file name. The AI Sprint annotation which enables the use of the drift detector is detectMetricDrift. Here we define which is the monitored metric, and then the statistical test to be executed together with its parameters like the test threshold, the detection interval, the monitoring period, and the data collection period. In the case instead the monitored matrix is in the drifted state, it stops the normal execution of the component and starts storing the input sequence to the local min.io bucket by appending the drift suffix to the file name. The forecasting LSTM component takes as input the output of the previous one, so the file name will have the notedrift suffix appended to it, and after loading the model, it performs the inference to forecast the next values. The very first step is the execution of the AI Sprint design tool to prepare the application for deployment. So we use the AI Sprint Studio image, and we give as the application directory the name of the application. After the design stage, the next step consists in running the Toscarizer to generate the images of the two components. If we inspect the generated containers YAML file, we can see that the images have been generated also for the drift detector. So the drift detector is the AI Sprint tool which is automatically added to the application for the deployment, and here we can see its implementation which has been automatically generated by AI Sprint. It uses a set of utility functions to read the values of the monitored metric from InfluxDB, then also to connect to the min.io client in order to store the state of the metric, and after the detection algorithm, and finally in the drift detector config YAML file we have a summary of all the drift detection parameters that have been defined by the user. Here finally we can see also the production deployment that will be used for the deployment stage. Before deploying the application, we must run the Toscarizer Tosca command to generate the Tosca files for the optimal deployment. And here we are going to generate the Tosca files, so for the identity and forecasting LSTM components. So if we are going to inspect the IM folder within the deployments directory, we can see the two generated files. Furthermore, we have also the multi-cluster quality of service constraints. Then, in the end, we have the deployment stage. So we use the deploy command of the Toscarizer to deploy the application, and in particular we are going to say to the Toscarizer that we are interested to deploy the optimal deployment. So let's inspect the HIME dashboard. So here we have the two infrastructures for the two components that have been correctly deployed. Once the application has been deployed, we are ready to demonstrate the goal of the drift detector. In order to do that, we use a specific Python script that periodically pushes the simulated time series windows to the input min IO bucket, which triggers the execution of the identity component. What we expect is that as soon as the sequences with the changed data distribution are fed to the application, the drift detector will detect the drift by changing the state of the monitored metric. If we inspect the status of the OSCAR services, we can see that the identity component is correctly executed as soon as a new window is uploaded to the bucket. Since at this stage no drift is occurring, the output of the identity function is stored to the output bucket with the noDrift suffix, and the forecasting LSTM is triggered. In the meanwhile, by logging in the InfluxDB, we can observe how the mean of the sequences is correctly stored at each execution. These are the values that are read by the drift detector and used as input to the statistical test. During its execution, the drift detector generates a log file. At the very beginning, we can see that the drift detector initializes the statistical test and stores at 0 as a metric state in a specific YAML file, which indicates that no drift is occurring. This is the file that the components use to get information about the drift state. After a while, the drift detector correctly recognizes the programmed drift and notifies the start of the data collection period. By looking to the drift state YAML file, now we have that the value of the mean metric is 1, indicating that its distribution changed. After the drift detection, we can observe how the output of the identity component is not stored in the output folder. Instead, it is stored in a specific drift detection data folder with the drifted suffix. After the end of the data collection period, the user can download all the collected data and use it to retrain the forecasting LSTM to adapt to the new distribution. After the retraining, the model is able to correctly predict the future samples given the new input sequences, and the application is ready to be redeployed.